Jacobian is computing inverse kinematics. So far, we have used fsolve to compute inverse kinematics. Okay. So here we'll use Jacobian to do that. Yes, how do you do that? First some theory, and then after the theory, I'll show you essentially code which does the same thing for a double pendulum. Just draw a simple curve, like say a circle. So here's some theory. So we know that the velocity of any point is the Jacobian of that point times q dot. This was derived somewhere in here. We derived this. I just took this expression j times q dot. See application 1. Computing linear velocity. Okay, so what we can do is we can write this as so remember, this is the Cartesian velocity. Okay, so and this is joint velocity. So what is the Cartesian velocity? Let's write this as let's just write it as let's say r dt equals j times d q dt. Okay, where r would be something like x, y, right? And q would have something like theta 1, theta 2, and so on, depending how many links you have. Okay, we can just multiply both sides by dt, so we get dr equals j times dq. Okay, we will just multiply both sides by j inverse. So j inverse dr equals, when you multiply j inverse times j, that will be identity, so just be dq. So we have dq is j inverse dr. Okay, so that's the key question. So the way you use it is we will write dr. What is dr? Dr is the change in the position. So we'll do this. We'll write this as r ref, that is the reference position. So for example, if you have a curve, let's say a circle, then you need it, a point on the circle is given by x ref, y ref, right? So that would be r ref. You subtract it from the measured position r, and then that will give you change in q, dq. So let's write this down. This is x ref, y ref, reference motion. This is x, y, actual position, and this is basically telling you the update in joint angle. So it's telling you how much, if the actual position of the end effector is not exactly at where you want it to be, then it tells you how much you need to change the angle. So we can just draw a figure to show that. So copy. So let's say you want to draw a circle, and let's say that this is RF. This is the actual position R. Remember, that's X ref, Y ref, and this is X, Y. So there's an error, right? Your end effector should be at the asterisk, but there's an error. So this part is dr. So what this formula is telling you is that in order for R to be close to Rf, you need to move the joint angle by dq, J inverse dr. So it's telling you you should move it perhaps like this. So this change is dq1, and then it's hard to show, this change is dq2, and dq is dq1, dq2. So if you change it, you'll have R going to Rf. And if you just keep doing that, so that's for one point, but if you keep doing that for all points, then you'll be able to trace whatever curve you want to trace. So that's the change. So what you need to do, the final step would be you'll take the old angle, theta1 being the angle of the first joint, and you'll add to it dq1, and then you take theta2, that will be your old theta1 plus dq2. So this is the new one, right? dq1 is just giving you the change. You need to compute what is the absolute change. So it will be what it was in the old configuration, that is theta1 old, theta2 old, and then add to that dq1, dq2. Okay, so let's see how this is put together in code. It's very similar to the previous one, the fsolve, except that instead of using fsolve to compute the change, you're just using this formula, dq, and then the update. So I have this file which I'll first run. People on Zoom, can you see Spider? Last time I had a problem with this. No, great. Don't see Spider. Can you see it now? Okay, perfect. Okay, let's run this code. And it's going to draw just a circle using the two links. Okay, and so that's the red is the actual, and then the blue, I think, is reference. Okay, so I'll quickly run through the code. How big is it? It's just about 130 lines. A big chunk of this code is actually doing the animation, which is see from 95, actually from 95 all the way to, so about a third of the code is just doing the animation. Okay, so what is done here is there are a few helper functions I wrote down. I initialize the angles. I do forward kinematics. So that function basically what it does is, all it does is if you given theta1 and theta2, it computes where the end effector is. And I specify some r and the center of that circle. And now I need to be a little bit careful. That is, I need to ensure that where I start is actually one of the one of the points on the circle, right? So you should ensure that the starting position is actually one of the points on the circle. If it is not, then it's going to do something crazy to begin with, and that will mess up everything. So that's one precaution you need to take. Okay. Now there is the for loop. This for loop runs through the entire points, the reference positions of the circle, and then just does this calculation of computing the Jacobian, which is a formula I wrote down. The Jacobian I did not write down, but it's going to be the Jacobian of the point we care about. In this case, the Jacobian of E, I said. E is basically the position of the end effector, the tip of the second link, or the tip of the blue link, which you saw. Then I take the inverse, and then it's just a matter of doing J inverse time dx here. Dx is dr, okay, from the notes. And then I just update theta1, theta2. That's it. That's all to it. And then you can see the function. So there is the Jacobian formula. There is sines and cosines are not defined, so I need to use numpy, and then the forward kinematics. So run it again. And then you can, of course, change the curve to be whatever you want. It's straightforward.